Hi, my name is Delaney Farrell, and I'm a third-year PhD student in the Computational Science Research Center. And my project is on deducing neutron star equation of state from observed X-ray spectra with machine learning. Neutron stars contain matter in one of the densest forms found in the universe, making them a unique astrophysical laboratory to study the structure of space-time and how matter exists at extreme conditions, so extreme that they're not replicable on Earth. Neutron stars can have masses up to twice that of our sun and radii between 10 and 15 kilometers. These stars can also rotate at extremely high frequencies, up to 43,000 times per minute. Depending on their mass and rotational frequency, the matter within the core of neutron stars may be compressed to densities that are up to a magnitude greater than the density of ordinary atomic nuclei. Because we can't physically look inside these stars, there are many open-ended fundamental questions about the structure of strongly interacting matter that exists within a neutron star, specifically regarding exotic particle formation, phase transitions, and deconfined quark matter existing within the inner core. These unanswered questions are the reason why a large number of models exist to describe the state of neutron star matter. The determination of a star's equation of state, or the thermodynamic relationship between pressure and energy density, is not only important to understand what happens on a microscopic level, but also on a macroscopic level. There's a one-to-one correspondence between a neutron star's equation of state and observable properties like mass and radius through the stellar structure equations, which are derived by Einstein's field equations and general relativity. These same observable properties can also be determined by observation of these stars from telescopes like the Chandra X-ray Observatory or NICER, meaning observable properties make a direct connection between astrophysical measurements and the microphysics of dense matter. How we arrive at observable properties like mass and radius of a neutron star from its equation of state is through a set of nonlinear partial differential equations referred to as the stellar structure equations. The simplest version of these equations are the Tolman-Oppenheimer-Volkoff or TOV equations shown here on the screen, which are used to describe spherically symmetric non-rotating stars. These equations take an equation of state as an input and output a curve in the mass and radius plane, where each mass and radius point is a potential star that could have that given equation of state. These stellar structure equations are invertible, but they require at least two mass and radius points known to exactly determine an equation of state. But what about observation? Most neutron stars are observed from their X-ray emission. The X-ray spectra from a star also determines observable properties like mass and radius through a process called spectral fitting. The image you see here on the right side shows 68 and 95% confidence intervals for the mass and radius of one star given its X-ray emission shown here on the left. This process is not invertible because of the uncertainties inherent with observation and spectral fitting. So there's no real first principle approach where X-ray spectra can determine a star's equation of state. The question of this research project is then, can we instead make this link using machine learning? So we approached this problem by first compiling a bunch of training data, which was comprised of variations of the GM1L equation of state and subsequent mass and radius pairs solved for with the TOV equations. And then we also generated X-ray spectra using a spectral fitting package called XSpec. As for network construction, we developed three networks intended to propagate realistic observational uncertainties. The first is direct regression by a neural network of equation of state from a spectra input. The second is a calibrated likelihood ratio estimate, also predicting equation of state from a spectra input. And the last actually goes the opposite way. It's a Poisson probability joint prediction of spectra from a mass and radius input. For more information on how we actually constructed the problem, you can come and visit me in my poster on April 8th. Here's a list of my collaborators, as well as some references. This work was funded by the two NSF grants listed on the bottom of the screen. And I'm also personally funded through the ACSESS scholarship from the Computational Science Research Center at SDSU. Thanks for listening.